Mars looks like the next step for humanity, but it may be one of the worst places to build a permanent future. The deeper you go into the science, the worse it gets. Weak air, constant radiation, toxic dust, fragile systems, and a planet that keeps turning survival into an engineering emergency. Mars is not a second home waiting for us. It may only be a crisis we can manage for a while. Most Mars stories start the same way. A crew lands, a habitat inflates, solar panels unfold, crops grow under glass. Step by step, a settlement begins. That opening sounds clean, but it starts from the wrong assumption. The wrong assumption is that the real problem begins after touchdown. It does not. The real problem begins with the system you're trying to settle. Mars is not just a cold place that needs better tools. It is a damaged planet inside a damaged environment. The atmosphere is thin enough to leave you exposed and thick enough to make landing difficult. Radiation reaches the surface at levels that force shielding into almost every serious plan. The soil is not friendly dirt. The dust is not just annoying weather. The gravity may still be too low for long-term human health, and the transport schedule is brutal. Earth and Mars line up for major mission windows only about every 26 months. That means every mistake is stretched across years, not weeks. Every shortage takes longer to fix. Every rescue plan is delayed by basic orbital mechanics. That is the first thing that needs to be made clear. Mars is not a frontier waiting for you to build normal life on top of it. It is a system that punishes small errors until they become major failures. And before you even get to the surface, one of the clearest warnings is already hanging over the planet. So what is the warning that most people ignore? It is Phobos. Phobos is usually treated like background detail. A small moon, an interesting rock, maybe a future mining site, maybe a future orbital station. But Phobos is not a decorative object in the Martian sky. It is one of the clearest signs that Mars is not a stable place to build permanent civilization around. Phobos orbits extremely close to Mars. It is only about 6,000 kilometers above the surface, around 3,700 miles. That is closer to its planet than any other known moon in the solar system. It moves fast enough to circle Mars in about 7.66 hours, which means it goes around the planet roughly 3 times during one Martian day. From the ground, it would not feel calm or distant the way Earth's moon does. It would move quickly. It would rise and set in ways that feel strange. Even visually, the Mars system already behaves differently from the Earth system people instinctively compare it to. And then there is the part that matters most. Phobos is not holding a steady orbit. It is slowly spiraling inward. The number sounds small at first, about 1.8 meters per century, roughly 6 feet every 100 years. On a normal human scale, that sounds almost irrelevant. But the point is not that Phobos is going to crash tomorrow. The point is that the orbital setup around Mars is not stable even on long time scales. Its inner moon is already moving in the wrong direction. Why does that matter for colonization? Because a real Mars civilization would never depend only on the ground. The moment Mars becomes more than a science outpost, orbit becomes essential. You need communication relays, you need navigation systems, you need observation platforms, you need cargo staging, you may need fuel depots, emergency shelters, transfer stations, and industrial support above the atmosphere. A serious civilization around Mars would depend on orbital infrastructure the same way modern civilization depends on shipping routes, power grids, and data networks. The idea that Mars colonization is only about building domes on the surface is far too simple. That is why Phobos matters so much. It is already inside the areosynchronous radius, the point where orbital behavior starts working against long-term stability for a moon like this. Tidal forces are pulling it down, not pushing it away. In plain language, Mars is draining orbital energy from Phobos and bringing it closer over time. So the very planet people want to turn into a permanent second home is already showing that its inner orbital environment comes with built-in instability. That does not mean nobody can use orbit around Mars. It means you cannot casually talk about permanence without admitting what kind of system you're working inside. And that is where a lot of Mars optimism starts falling apart. It keeps using language like settlement, expansion, and city building, while quietly assuming the surrounding environment will behave like a stable foundation. It will not. Then the stakes get even bigger, because Phobos is only one layer of the problem. The atmosphere is too thin to protect you properly from radiation, temperature swings, and pressure loss, but it is still thick enough to create enormous difficulty during entry, descent, and landing. That means Mars gives you almost the worst combination possible. There is enough air to burn and destabilize incoming spacecraft, but not enough air to slow large human cargo safely on its own. So even reaching the surface is a repeated engineering bottleneck, not a solved transportation route. Then once you land, the same atmosphere still does not give you what a colony actually needs. It does not shield like Earth's atmosphere. It does not hold the heat like Earth's atmosphere. It does not let you breathe. It does not support open-air living, open-air farming, or ordinary outdoor work. Every habitat has to act like its own artificial planet. Pressure, oxygen, temperature, water recycling, contamination control, radiation mitigation, and power all have to be continuously managed. Nothing about that is casual, and nothing about that becomes normal just because the first few missions succeed. Then there is the surface itself. The soil contains perchlorates and other chemistry that make simple farming stories misleading. The dust gets into seals, joints, optics, filters, and power systems. Radiation keeps building dose over time. Gravity may still be too low to protect bone and muscle, development, and long-term health over generations, and every one of those problems connects to the others. Dust affects power. Power affects life support. Life support affects water extraction. Water extraction affects fuel, air, hygiene, and agriculture. Agriculture depends on controlled environments because the soil is hostile and the outside world is lethal. That is the real thesis. Mars colonization fails because the problems do not stay separate. Every layer compounds the next one. Phobos is decaying. The orbital environment is warning you early. The atmosphere is too thin to shield you and too thick to ignore. The soil is chemically hostile. Radiation builds up over time. Dust attacks machinery and power. Gravity may still damage the human body in ways nobody has fully solved. So when people use the word colony, the word sounds bigger and stronger than the actual evidence supports. A colony is supposed to mean permanence, growth, stability, ordinary life continuing without constant emergency conditions. Mars does not give you that. Mars gives you a highly managed outpost where survival depends on uninterrupted engineering, uninterrupted maintenance, uninterrupted supply logic, and very little room for failure. That is why the colony was doomed before the first habitat inflated. Not because no one can land there, not because short missions are impossible, but because the thing being promised and the thing the data support are not the same. What gets advertised is a future society. What the science keeps describing is a fragile outpost on life support. And once that gap is clear, the next question gets worse, because Phobos is not just falling. It may already be telling you that Mars is the wrong place to build anything meant to last. A moon that goes around its planet in less than 8 hours should already make you stop and rethink the whole Mars story. Phobos circles Mars in about 7.66 hours. That is so fast that it can move across the sky faster than a human work shift. On Earth, your moon feels slow, distant, steady. It rises, hangs there, and sets with a kind of calm that feels normal because we grew up with it. Phobos would not feel normal at all. It is so close to Mars and moves so quickly that from the surface it behaves nothing like the moon people instinctively compare it to. That matters because it tells you right away that Mars is not part of some calm Earth-like planet-moon setup. It is a different kind of system entirely. Phobos sits only about 6,000 kilometers above the Martian surface, around 3,700 miles. In space terms, that is extremely low. It is basically hugging the planet. And because it is so close, it races around Mars again and again while the planet turns below it more slowly. That alone changes the whole feeling of the sky above a future settlement. The nearest moon is not some distant stable companion. It is a small body moving too fast, too low, and too close for anyone serious about permanence to casually ignore. So why is that such a bad sign? Because the way Phobos moves is telling you exactly what Mars is like to build around. Phobos orbits below the synchronous altitude of Mars. In simple language, that means Mars rotates more slowly than Phobos circles it. On Earth, our moon is far enough out that tidal effects slowly push it away from us over time. Phobos gets the opposite treatment. Mars is pulling energy out of its orbit and dragging it inward. So this moon is not just close, it is on the wrong long-term path. That is the part most Mars optimism skips over. People hear moon of Mars and quietly translate it into future asset. They picture a fuel depot there, a mining base, a cargo hub, maybe even a safer place to build first before committing to the surface. But the moon itself is telling you that future asset is not the full story. This is a body already being pulled down by the planet it orbits, and the end state is not subtle. On long timescales, Phobos is expected either to crash into Mars or break apart into a ring. That is the trajectory. NASA's Mars-Moon descriptions have laid out that rough endgame on timescales around 30 to 50 million years, with broader estimates stretching across tens of millions of years more. And this is where people often make the wrong move. They hear millions of years and mentally file it under not relevant. But that misses the whole point. The reason Phobos matters is not because the first settlers are going to stand outside and watch it fall apart. The reason it matters is because it reveals the kind of system Mars really is. A planet headed towards stable long-term development does not have its innermost moon slowly losing orbital ground on the way to destruction. That does not mean Mars cannot host missions, stations, or even long stays. It means the system itself is not naturally trending toward the kind of permanence people smuggle into the word colony. That word is doing a lot of dishonest work. Colony sounds like continuity, growth, expansion, something that gets stronger over time and settles into routine. But Phobos points in the other direction. It says the Mars system is not built around stable forever structures. It is built around decay, maintenance, and long-term instability that you have to constantly engineer around. And that matters even if your time horizon is much shorter. Say you want Phobos to be a major part of Mars civilization. Say you want it to be a forever port where ships arrive and leave, a forever mine where you extract material, a forever hub where communications, navigation, cargo transfer, and emergency infrastructure all connect. Phobos itself tells you that forever is the wrong frame. The body is not on a timeless orbit. It is on a countdown. Slow, yes, but real. And if the object you want to treat as permanent strategic high ground is already being pulled inward by the planet, then Mars is warning you early that permanence will always be something you force, not something the system gives you. That is the deeper scale of the problem. Civilization does not only depend on whether danger arrives tomorrow, civilization depends on whether the environment supports long-term confidence. Oceans let Earth build shipping, stable orbits let Earth build satellite systems, predictable conditions let infrastructure accumulate instead of constantly fighting to stay functional. Mars keeps failing that test. Not always in one dramatic way, but in the worst possible way for settlement, by making every layer slightly less trustworthy than people want it to be. And Phobos is one of the clearest examples, because the numbers are so strange and the meaning is so direct. A moon this low, this fast, and this doomed is not just an astronomy fact, it is a structural warning. It tells you Mars is not a place where the sky itself feels settled. The inner moon is already on borrowed time. That changes how you should read every futuristic Mars concept. A clean orbital network around Mars is not guaranteed peace and stability. A permanent industrial ring of infrastructure around the planet is not resting inside some naturally friendly system. It is being built around a world whose nearest moon is already moving toward eventual destruction. Again, that does not make all use of Mars' orbit impossible. It makes casual language about permanence sound weak and unserious. And that is why Phobos works so well as the central idea for this whole argument. Mars is often sold as the next step for civilization, the place where humanity becomes multiplanetary and starts building something that lasts. But one of the first major things you see in that sky is a body that is physically telling you the opposite. This system does not promise stability. It promises degradation over time. On Earth, the moon feels like part of a long-lived arrangement. It shapes tides, lights the night, and feels constant on the scale of human life and history. On Mars, the inner moon does not feel like a guardian or a companion. It feels like a warning. The sky over a future colony is not quietly reassuring you. It is showing you a body that is too close, too fast, and moving the wrong way. And once that sinks in, the tension gets worse, because orbital decay is only one part of the problem. The next question is even more uncomfortable. If Phobos is being pulled inward, is it at least a solid, reliable object while that happens? That is where the story gets darker, because Phobos may already be coming apart. A moon that is falling inward would already be a problem. A moon that may already be cracking while it falls is much worse. Up to this point, the danger sounds like orbital mechanics, numbers, timescales, slow decay. But with Phobos, the problem is not only where it is, the problem is what it may already be becoming. Close-up spacecraft images show long grooves, fractures, and surface features stretched across the moon. These are not tiny marks you need a specialist to care about. They are big enough to change how you think about the body itself. And NASA has highlighted modelling that links many of those features to tidal forces from Mars. In simple terms, the same gravitational relationship that is pulling Phobos inward may also be stressing the moon physically. That changes the whole tone. This is no longer just a moon on a bad long-term orbit. This is a moon that may already be showing the strain in its own surface. The warning is not hidden in a spreadsheet, it is written into the ground. So why does that matter so much for Mars colonization? Because people do not just talk about Phobos as a scientific curiosity, they talk about it like future infrastructure, a depot, a staging base, a mining site, a shipyard, a safer place to operate from than the Martian surface. That is the fantasy version. The real version is a small moon with visible structural weirdness sitting extremely close to Mars, under continuous tidal stress, while slowly spiralling downward over time. And once you add size to the picture, it gets even harder to sell as stable high ground. Phobos has an average diameter of about 22 kilometers, around 14 miles. That is tiny. It is not a large world with deep geological reserves of stability. It is not a major moon like our moon. It is not some large body where you can assume big internal strength and a lot of margin for damage. It is a small battered object. And small bodies do not handle stress the way planets do. That matters because size changes everything in space engineering. A larger body can spread stress across more material, more depth, and more structure. A small body can be much more vulnerable to cracking, reshaping, and mechanical weakness. If Phobos really is being stressed by tides from Mars, then you're not dealing with a strong orbital platform that just happens to have a strange path. You're dealing with a small object that may be physically responding to the forces acting on it. That is a bad candidate for permanent strategic use. And notice how the pattern keeps repeating. Every time Mars advocates try to move the dream somewhere safer, the new location starts breaking down too. The surface is harsh, so people look to orbit. Orbit feels exposed, so they look to Phobos. Phobos sounds useful, so they picture bases, depots, and industry there. But then the moon itself starts looking unstable. The closer you inspect the supposed backup plan, the more it starts looking like another object that needs careful handling, continuous monitoring, and major engineering just to be trusted at all. Then the science gets even more interesting, and for this argument, even more damaging. Not every groove and fracture on Phobos has one single agreed explanation. Some patterns may be linked to tidal stress from Mars. Some may also be explained by re-impacting ejecta and secondary cratering. In simple language, debris blasted off the moon or nearby impacts may have fallen back and reshaped parts of the surface. That means scientists are still working through how much of what we see comes from tidal stretching, how much comes from impact-related reworking, and how much comes from both acting together over time. And that does not weaken the point, it strengthens it. Because either way, the moon is not becoming simpler or safer. If those grooves mostly record tidal stress, then Phobos is a moon visibly strained by the same forces pulling it downward. If they mostly record impacts and re-impacting debris, then Phobos is a surface shaped by repeated violence and mechanical disturbance. If both explanations matter, then the picture is even more complicated. None of those outcomes give you a calm, quiet, predictable platform for major permanent infrastructure. That is the key point to keep straight. You do not need every scientist to agree on one exact cause for every groove to know that Phobos is not a normal construction site. It is a mechanically complicated rubble world with a history of impacts, fractures, rearrangement and stress. That is not the kind of place you casually label a forever hub. And this is where the public picture of Mars colonization keeps getting ahead of the science. A lot of future Mars concepts quietly assume that Phobos can function like a clean orbital service station. They place depots there, they place shipyards there, they place heavy logistics there. Sometimes they even treat it like the safer first step for people, because it avoids the dangers of landing directly on Mars. On paper that sounds practical. In reality, a body this small, this fractured, this close to Mars, and this likely stressed by tidal forces is not a calm platform. It is a suspect platform. That does not mean nothing can ever operate there. It means the confidence level is much lower than the fantasy version admits. A small moon under stress is not where you want to casually anchor the future of a whole planetary system. If your long-term Mars civilization needs Phobos to be reliable, the moon itself is already pushing back against that assumption. And notice what that does to the emotional center of the whole Mars story. People often frame Mars as a place where the hard part is the surface. Get through landing, build enough habitats, bring enough machines, and you can slowly expand. But when even the nearby moon starts looking structurally questionable, the feeling changes. The problem is no longer that Mars is difficult. The problem is that nowhere around Mars feels normal enough to support the word permanence without a warning attached to it. That is the tone shift this section needs. Before touching the ground, before dealing with dust storms, radiation, toxic soil or thin air, your supposed safer alternative in orbit is already geologically and dynamically suspect. It is not just that Mars is hard to live on. It is that the broader Mars system keeps removing the clean options one by one. You want a stable orbital base? Phobos may be too stressed and too small. You want a dependable logistics hub. It may be on a body already marked by fractures and mechanical uncertainty. You want high ground above the planet that feels safer than the surface. That high ground is attached to a moon that may already be showing the effects of being in the wrong orbit around the wrong planet. And that is why this part matters so much. Phobos is not just falling. It may already be coming apart in ways that make the entire idea of a neat, orderly Mars support network look much weaker. The moon is not offering safety. It is offering another engineering problem. Once that is clear, the next step gets worse again. Because if Phobos eventually breaks apart instead of simply crashing, then the danger does not stay on the moon. It spreads into the space around Mars itself. A ring around Mars sounds beautiful until you ask one simple question. What happens when beauty is made of debris moving through the same space your civilization needs to use? That is where the problem stops being about one moon and starts becoming about the entire orbital environment around Mars. Right now, Mars has no rings, but the long-term fate of Phobos is not just impact or disappearance. One serious possibility is that it breaks apart and forms a ring around the planet. People hear that and think of a dramatic sky, a historic moment, a more exotic version of Saturn. But that reaction only works if you forget what a real Mars civilization would actually depend on. A mature Mars settlement would not live only on the ground. It would depend on orbit constantly, communication relays, navigation satellites, observation systems, cargo traffic, surface-to-orbit transport, fuel depots, transfer stations, emergency support. A serious Mars economy would need clean and predictable orbital lanes the same way modern civilization needs clean and predictable shipping routes, air traffic corridors, and data networks. So the moment you translate a future ring into colony terms, it stops sounding beautiful and starts sounding dangerous, because a ring is not decoration, a ring is material, a ring is particles, a ring is debris sharing orbital space with infrastructure you cannot afford to lose. That is the jump in stakes. Phobos is not just a moon with a bad future. Phobos may eventually turn part of the Mars system into the exact kind of environment a high-tech settlement would hate most: cluttered, collision-prone, and harder to manage over long periods. So what does that actually mean in practical terms? It means the problem is not one dramatic breakup event and then everything goes quiet. The problem is what comes after. Rings are made of countless particles. Some can be dust-sized, some can be larger. But even a mostly dusty torus around Mars would still matter, because infrastructure in orbit does not need a giant boulder to fail. Long-term collision risk comes from persistent particle environments, repeated exposure, uncertainty in orbital distribution, and the fact that high-speed impacts do not need much mass to do damage. If you're trying to keep satellites alive, protect transports, maintain relays, or run routine traffic around Mars, you want the orbital environment to be as clean and predictable as possible. A ring is the opposite of that. And this is not only about some far future cinematic destruction scene. Earlier observations and scientific discussions have already looked at the possibility of dust or gas concentrations associated with the Phobos orbit. That matters because it pushes the whole idea away from fantasy and back into engineering. The concern is not only that Phobos has an end state. The concern is that the space around it is already the kind of space where debris behavior matters. That is why the ring scenario should be understood as contamination of the orbital environment, not just a pretty sky change. Once you say it that way, the danger becomes much easier to understand. A colony can survive dramatic events more easily than it can survive persistent background failure. One explosion is obvious, one impact is visible. A long-duration debris problem is worse in a different way. It slowly makes routine operations harder, riskier, and more expensive. It adds uncertainty where civilization needs repetition and trust. And civilization at Mars would need repetition more than anything. People talk about Mars settlement like it is a one-time breakthrough. Land once, build once, succeed once. Real settlement is the opposite. It is thousands of repeated actions that all have to keep working. Launches, landings, cargo runs, surface support, orbital transfers, satellite replacement, emergency response, mapping, communication, maintenance, expansion. The only way a Mars colony begins to look stable is if that larger system starts feeling routine. A dusty, hazardous orbital environment works directly against that goal. So this is why Phobos decay matters so much more than it first seems to. It is not just an interesting moon fact. It is a warning about the future of the whole Mars system. The colony fantasy assumes scale. It assumes traffic. It assumes regular cargo movement and industrial build-up. It assumes there will be enough confidence in orbit to keep stacking more infrastructure there. But the deeper Mars civilization goes, the more orbit matters, and the more a ring-forming inner moon stops being trivia and starts becoming a civilizational risk. That is the connection back to the core idea. Mars is often presented as a place where hard work turns difficulty into permanence, but Phobos points the other way. It says even the sky above your colony can become part of the hazard, and that should change how you hear big promises about the future. A forever port in Mars orbit, a forever logistics hub, a forever industrial chain between ground and space. Those promises depend on the orbital neighborhood staying manageable. Phobos says that assumption comes with an expiration date. Maybe not on a human timescale, maybe not on the timescale of the first outpost, but still real, still built into the system, still the opposite of the natural stability people want Mars to have. This is where deep time stops being abstract science and turns into design philosophy. No, the first settlers are not going to look up and watch Phobos turn into a ring. That is not the point. The point is that the existence of that end state tells you how Mars must be understood from the start. You would never design a permanent civilization while pretending the long-term dynamics of its orbital neighborhood do not matter. You would not call a place naturally stable if one of its most important nearby bodies is on a path toward breakup or destruction. You would treat that as a sign that permanence on this world will always be engineered against the grain, never supported by the environment itself. That distinction matters. It does not prove settlement is impossible. It does prove that Mars is not a naturally stable second Earth, and that is a much more serious statement than just saying Mars is difficult. Earth gives civilization a lot of hidden support, stable conditions for large-scale infrastructure, a planetary environment that, despite all its dangers, broadly allows traffic, communication, resource movement, agriculture, and orbital development to scale together. Mars does not give you that same base. On Mars, the atmosphere works against you. Radiation works against you, surface chemistry works against you, dust works against you, and even the orbital neighborhood comes with its own long-term timer. That is why the ring of Mars is not a cool visual in this story. It is the future shape of a problem. It is what happens when a decaying moon stops being just a moon and starts threatening the space your civilization depends on. The closer Mars gets to becoming industrial, the more that matters. The more assets you place in orbit, the more valuable clean orbital space becomes. The more valuable clean orbital space becomes, the more dangerous any long-lived debris environment becomes. And once that logic is clear, the next problem becomes unavoidable. Even if orbit were perfect, you still have to get down to the surface over and over again. And Mars is one of the worst places in the solar system to do that at human scale. Getting to Mars is hard. Getting down to Mars is worse. And this is where a lot of Mars optimism quietly breaks, because people talk about reaching Mars like the main challenge is the long flight through space. It is not. One of the biggest bottlenecks starts when you arrive. Mars is famous for entry, descent, and landing for a reason. Its atmosphere sits in almost the worst middle ground you could design for human cargo. It is extremely thin, far thinner than Earth's, but it is not thin enough to ignore. So when a spacecraft hits it at interplanetary speed, the atmosphere still creates major heating. You still need heat shields, you still need aerodynamic braking, you still need to survive enormous stress during the drop. But the atmosphere is also too weak to slow a heavy spacecraft all the way down safely by itself. That is the trap. There is enough air to burn you, but not enough air to save you. That one fact changes everything. People sometimes talk about Mars landings like they are just moon landings with more difficulty added on top. That is wrong. The moon has almost no atmosphere, so the problem is mostly controlled propulsion. Earth has a thick atmosphere, so the problem can lean much more on aerodynamic braking and parachutes. Mars gives you the bad middle case. You slam into an atmosphere thick enough to create serious heating and chaos, but too thin to finish the job for large payloads. So the whole descent becomes a chained sequence of systems that all have to work almost perfectly, one after another, under extreme time pressure. And that brings you to the number that still defines this problem better than almost anything else: 7 minutes. NASA JPL called it the 7 minutes of terror because from the top of the Martian atmosphere to the surface, a spacecraft has to go from about 13,000 miles per hour, around 21,000 kilometers per hour, to zero in roughly 7 minutes. Not later, not gradually, right then. And it has to do it essentially on its own, because Mars is too far away for real-time human control from Earth. By the time a signal gets back telling engineers something went wrong, the spacecraft has already either landed or crashed. That is already hard when the payload is robotic and only a few metric tons. It is already hard when the system is designed around years of testing, narrow mission goals, and the acceptance that a failed robot is tragic but not morally the same as a failed crewed landing. Now scale that up to human missions. Bigger vehicles, heavier cargo, life support systems, surface habitats, power systems, spare parts, construction equipment, return propellant systems, medical supplies, radiation shielding, food, water processing hardware. Suddenly you are not landing a rover, you are landing the mass needed to keep people alive. And the larger the landing system gets, the more this entire problem becomes dangerous in new ways. That is why the phrase "just scale it up" stops being serious here. Scaling up is exactly the part that has not been solved. Mars landing history is already rough even with robots. NASA's Moon to Mars planning material has noted that only 12 out of 19 attempted robotic Mars landings had been successful. That is the context people skip when they talk about future cities on Mars, as if the transport layer is mostly handled. This is after decades of learning, after major advances in heat shield design, parachutes, radar systems, guided entry, terrain relative navigation, sky crane systems, and deep institutional experience. And even then, Mars has kept killing missions. That matters because a colony is not one heroic landing. A colony is repetition. A colony means landing again and again and again. First a few robotic cargo missions, then habitat components, then power systems, then crew, then resupply, then heavier industrial equipment, then replacement parts, then expansion modules, then medical support, then backup systems for the backups. The moment you stop thinking in terms of one historic mission and start thinking in terms of actual settlement, the landing problem grows into something much more serious. You're not trying to win one difficult event, you're trying to turn one of the hardest landing environments in the solar system into a routine transportation corridor. And Mars does not reward routine, it punishes it. Because every arrival is another pass through that same atmospheric trap. Every arrival has to survive heating, drag uncertainty, deceleration, navigation, and final touchdown in a world where the atmosphere does not help enough and the time window for correction is brutally short. If one landing fails during early exploration, that is a mission loss. If one landing fails in a mature settlement, that could mean loss of critical cargo, life support equipment, fuel production hardware, or the crew themselves. Once the colony depends on regular arrivals, landing stops being just a technical challenge and becomes a civilizational vulnerability. That is the real pressure point. A city on Earth can survive because roads, ports, aircraft and supply chains operate at massive scale, with high repetition and tolerable failure rates. A Mars colony would need that same basic logic of repeated arrival, but on a planet where each landing still looks like a high-risk precision event. That is not a normal foundation for growth. That is a bottleneck built into the front door, and the mass problem makes it even harsher. Curiosity, one of the most famous Mars successes, had a landing mass around 3.3 metric tons. That is impressive for robotic exploration. But human-class cargo is in a completely different category. Once you start talking about payloads above 20 metric tons, you are no longer extending a proven system by a small amount. You're crossing into a different regime. NASA's own entry, descent and landing documents have been clear that crewed Mars missions will require major advances in deceleration, precision landing and access to the surface. In other words, the bridge between successful robotic Mars landings and real human settlement hardware is not short and it is not built yet. That gap is easy to underestimate because people see successful rover videos and assume the core problem is solved. It is not. A rover mission proves you can land something. It does not prove you can land enough, often enough, cheaply enough, and safely enough to support human permanence. And that distinction changes the whole Mars conversation. Because before you even get to radiation, dust, low gravity, toxic soil, or the economics of survival, you still have to pay the entrance fee every single time. Mars keeps charging it, every cargo load, every replacement system, every crew rotation, every expansion step. The colony does not only have to survive on Mars, it has to keep arriving at Mars. That makes the landing problem more than an engineering issue. It becomes a structural limit on growth. If each arrival remains difficult, expensive, mass-constrained and risky, then the settlement stays fragile no matter how advanced its plans look on paper. It may have big ambitions, but every ambition still has to pass through the same violent 7-minute funnel. So when people say Mars colonization will happen once transportation becomes reliable, That sentence sounds reasonable until you ask reliable at what scale. Reliable enough for one flagship mission is not reliable enough for a settlement. Reliable enough for occasional cargo is not reliable enough for a civilization. And reliable enough for civilization is exactly what Mars entry, descent and landing has never demonstrated at human scale. That is why this section matters so much. Before the colony fails from biology, dust, psychology or economics, it may fail because the planet simply makes arrival too punishing to normalize. Not impossible once, punishing every time, and once you do get down safely, the next false comfort appears immediately. People hear that Mars has an atmosphere and think that must help. It does help a little, just enough to make everything harder. Mars has an atmosphere, and that sounds helpful until you look at what that atmosphere actually does. A lot of people hear the word atmosphere and relax too early. Atmosphere sounds like protection. It sounds like weather, pressure, maybe it's something you can work with. On Earth, atmosphere means a real planetary shield. It spreads heat, slows temperature swings, supports flight, blocks a lot of radiation, and makes open-air life possible. Mars does not give you that. Mars gives you something much weaker. The Martian atmosphere is mostly carbon dioxide, around 95%. But composition is not the first problem. Pressure is. At the surface, Mars sits at roughly 1% of Earth's atmospheric pressure, usually only a few to around a dozen millibars depending on the location and season. That is not a real working atmosphere in the human sense. That is closer to a thin chemical trace wrapped around a planet. It is enough to exist. It is not enough to protect you in the ways people instinctively assume. That is why Mars can sound deceptively safer than it is. People hear there is air and quietly translate that into not a vacuum, so may be survivable with the right gear. But this is not almost Earth. This is not a rough mountain climate with bad storms. This is a world where the outside environment is still so thin that unprotected human life is completely out of the question. You are not stepping into harsh weather. You are stepping into an environment that barely counts as atmospheric cover at all. So what does that thin air actually mean when you're trying to live there? It means the atmosphere does a terrible job holding heat. On Earth, the atmosphere helps smooth out temperature changes and retain energy. Mars is much worse at that. Heat escapes easily. Day and night can be brutally different. Conditions swing hard because the atmosphere is too thin to act like a real thermal buffer. That means surface survival is never just about breathing. It's always about pressure and temperature at the same time. And that changes the whole idea of a habitat. A Mars habitat is not just a house with oxygen tanks. It is not just a sealed building with a heater. It has to act like a tiny artificial world. It has to create pressure that Mars cannot provide. It has to create thermal stability that Mars cannot provide. It has to manage air composition, humidity, heat retention, water recycling and contamination control all the time, without long interruptions, because outside the walls there is no forgiving environment waiting to catch you if a system drops offline. That is one of the biggest misunderstandings in the entire Mars discussion. People picture the outside world as hostile but still usable with enough protective clothing. In reality, the inside becomes everything. Your habitat is not shelter from bad weather. It is a full-time substitute for a missing planet. Every room, every corridor, every greenhouse, every airlock is part of an artificial environment that has to keep running correctly all the time. If it stops, Mars does not help. Mars finishes the job, and then the atmosphere gets even worse because it is not even stable over the course of the year. Mars does not hold a steady amount of atmospheric gas from season to season. A significant fraction of its carbon dioxide atmosphere actually freezes onto the poles during colder parts of the Martian year, and then returns to the atmosphere later by sublimating back into gas. In simple language, part of the atmosphere literally migrates in and out of the air as the seasons change. That means surface pressure can vary by around 30% through the Martian year. That is excellent planetary science. It is terrible infrastructure news. Because now the problem is not just that the atmosphere is weak. The problem is that the weak atmosphere changes noticeably over time. Pressure shifts, aerodynamic behavior shifts, dust transport conditions shift, thermal behavior shifts. And all of that happens on a planet where the atmosphere was already barely useful to begin with. That matters much more than it first sounds. Engineering loves predictable background conditions. It does not need perfection, but it needs ranges you can design around with confidence. On Mars, the air is already thin enough to make entry, descent, and landing difficult. And then even that thin air changes with the seasons. So the planet keeps doing the same thing over and over. It gives you partial help, then adds another complication on top of it. That pattern shows up everywhere. The atmosphere is thick enough to move dust, but not thick enough to give you comfortable aviation. Thick enough to heat an incoming spacecraft, but not thick enough to land heavy cargo safely on its own. Thick enough to matter for operations, but not thick enough to protect your body the way a real atmosphere should. You cannot rely on it, and you also cannot ignore it. That is exactly why Mars is so hard to turn into a place of normal life. A normal civilization needs the environment to do at least some of the background work for free. Earth gives you a breathable atmosphere, manageable surface pressure, large-scale thermal moderation, weather you can often survive outdoors, and enough shielding that daily life is not built around constant environmental compensation. Mars gives you the opposite. It makes you build the compensation first and then live inside it. So when someone says Mars has an atmosphere, the correct response is yes, but not enough of one when it actually matters. Not enough for Earth-like flight across the planet. Not enough for open-air farming. Not enough for ordinary weather protection. Not enough for meaningful radiation shielding. Not enough for unpressurized outdoor work. Not enough to turn a human settlement into something even remotely close to normal surface civilization. And yet there is still enough atmosphere to make serious trouble. Enough for dangerous entry heating. Enough for wind-driven dust movement. Enough for seasonal pressure cycles that affect operations. Enough to complicate every arrival from space. Enough to push fine dust into machinery and across infrastructure. Enough to create consequences without giving you the benefits you want in return. That is why the Martian atmosphere is not your shield. It is barely a filter. And that line matters because it breaks another common Mars shortcut. People want to believe atmosphere means progress. A little air now, maybe more later. A small advantage that engineering can eventually expand. But right now, for the real colony question, the atmosphere works more like a permanent half solution. It helps just enough to force complex engineering and not enough to remove the danger. That makes it one of the most Mars-like features of the entire planet. Partial help, full consequences. You cannot breathe it. You cannot trust it to warm you. You cannot trust it to shield you. You cannot trust it to stay constant. But you still have to account for it in every landing, every dust event, every thermal model, every habitat design, and every long-term surface plan. That is not an ally. That is another system burden. And once you strip away the comforting word atmosphere, the next problem becomes much harder to ignore. Because if the air is too thin to shield you properly, then something else is hitting the surface much more effectively than most people want to think about. That is where Mars stops feeling cold and empty and starts feeling biologically expensive every single day. Mars does not need storms or explosions to hurt you. It can damage you quietly every day, while the ground around you looks completely normal. That is what makes radiation on Mars so dangerous. You cannot see it. You cannot feel it building in real time. There is no dramatic warning in the sky most of the time. The landscape can look calm, the habitat can look secure, and the damage is still happening in the background. That is why the number matters so much more than the scenery. Curiosity's radiation instrument measured an average surface radiation environment at Gale Crater of about 0.67 millisieverts per day during its 2012 to 2013 measurements. NASA compared that to a typical chest X-ray of about 0.02 millisievert. Put that into normal language and the problem gets very clear very fast. A day on Mars is not some tiny extra health cost you shrug off. A week on Mars adds up quickly. A month adds up even more. The exposure is steady, and steady is exactly what a colony cannot escape from. That is why the idea of simply living on the surface starts breaking down. The second radiation enters the conversation. On Earth, background radiation exists, but it is managed by the fact that Earth actually protects you. Mars does not protect you that way, so the biological cost is not occasional. It is built into daily life, and daily life is the real test, not one heroic mission. A mission can accept risk for a limited time. A colony is supposed to turn exposure into routine. People sleep there, work there, repair equipment there, raise food there, maybe one day raise children there. Radiation changes the meaning of all of that. It turns every ordinary day into one more addition to a long-term health bill. That bill does not care whether the view outside looks historic or whether the mission patch looks impressive. It keeps growing anyway. Then the problem gets worse before anyone even reaches the surface. Mars is dangerous on the ground, but the trip there is even harsher in some ways. Curiosity's cruise measurements showed about 1.8 millisieverts per day during the journey to Mars. NASA planning discussions have cited about 0.66 sievert for a 360-day round trip under those conditions. That is a huge point, because it means the colony problem starts before touchdown. Your settlers do not arrive fresh and fully protected. They arrive after months in deep space already carrying radiation damage from transit. They arrive pre-exposed before they unload a habitat, before they grow food, before they repair a single valve or fix a single airlock. The opening move in Mars colonization is already biological wear. That changes the emotional center of the whole idea. People like to picture Mars as a challenge that begins when boots hit red soil. But a lot of the damage starts in the spacecraft. The trip itself is part of the hazard. So the colony is not built by perfectly healthy pioneers landing on a hard world. It is built by human bodies that have already taken a hit on the way in. And then you have to ask the obvious question: why is Mars this bad at protecting you in the first place? Earth gives you two huge defenses that people rarely appreciate until they imagine losing them. First, Earth has a thick atmosphere. Second, Earth has a global magnetic field. Those two layers do a massive amount of invisible work for life every single day. The atmosphere blocks and reduces a great deal of incoming radiation. The magnetic field helps deflect charged particles from the solar wind and other space weather effects. We live under that protection so constantly that most people barely think about it. Mars does not give you those defenses in the same way. Its atmosphere is far too thin to do Earth's job, and it does not have a global magnetic shield like Earth's to stand between the surface and the radiation environment of space. That is not a small detail in a planetary comparison. That is one of the biggest reasons Mars is scientifically fascinating and biologically hostile at the same time. And the history matters here too. NASA's MAVEN mission has spent years showing that solar wind stripping is part of how Mars lost so much of its atmosphere over time. NASA has reported present-day atmospheric loss rates of around 100 grams per second on average, with that loss increasing during solar storms. In plain language, Mars is not just a world that once became exposed. It is a world whose exposure is connected to the same long-term story that made it thin, dry, and vulnerable in the first place. That is why the danger feels so built in. Mars did not simply end up a little underprotected. It became the kind of planet where the protective layers that matter most were reduced over immense time. The same planetary history that makes Mars exciting to study also helps explain why it is so hard to survive on. So when people talk about living on Mars, the radiation issue immediately starts pushing that phrase in a much less glamorous direction. Because once you take the numbers seriously, surface living stops looking like standing around in habitats with wide windows and nice views. It starts looking like shielding math. How much material over your head? How much regolith piled onto the habitat? How much time spent outside? How much storm shelter capacity? How much exposure has each crew member already accumulated during transit? How much more can they safely take over months and years? Those are not side questions. Those become central design questions, and that is where the whole image of a Mars city starts changing shape. The fantasy version loves open structures, clear domes, and sunlight pouring through glass. Radiation engineering does not love that. Radiation engineering wants mass between people and the sky. It wants regolith cover. It wants heavily shielded zones. It wants underground spaces. It wants lava tube concepts explored seriously. It wants shelters inside shelters for solar events and long-term protection. The more honest the engineering becomes, the less the settlement looks like a shining frontier town, and the more it starts looking like protected infrastructure hidden under dirt. That is not an aesthetic complaint. That is the logic of survival. If the surface keeps billing your body every day, then living on Mars quickly turns into burying yourself on Mars. Not as a dramatic line, but as a practical one. You start covering habitats. You start favouring underground space. You start limiting exposure. You start building around dose limits, not around romance. Windows become a luxury. Shielding becomes the rule. And that is one of the hardest truths in the whole Mars discussion. The more seriously you take the science, the more the dream compresses. Wide-open colony imagery gets replaced by enclosed, shielded, carefully monitored survival space. Not because engineers lack imagination, but because radiation keeps forcing the design in the same direction over and over again. So this is not just one more hazard on a long list. Radiation changes the shape of the colony itself. It changes where people can live, how often they can work outside, how long they can stay, how healthy they can remain, and how much infrastructure has to exist just to reduce a threat that never fully goes away. And once you accept that, the next problem gets even more practical. Because even if you hide from the radiation, Mars still has another way to attack every system you bring with you. It does not arrive as an invisible dose. It arrives as fine red dust that gets into everything. Opportunity did not die because of one dramatic crash. It died because Mars blocked the light long enough to shut the mission down. That is the right way to start this part, because it removes the last bit of comfort people still attach to the word weather. Mars dust storms are not background visuals. They are not just something that makes the sky look dramatic. They have already ended real missions. Opportunity stopped communicating after a severe Mars-wide dust storm in June 2018. The storm began as a regional event and then expanded until it wrapped around the planet. The sky darkened so much that the rover's solar power could not recover. That is what weather means on Mars. It is not a delay, it is direct pressure on survival. And that matters because Opportunity was only a rover. A colony would be much more complex and much more dependent on stable systems. If dust can take down a robotic mission by cutting power and visibility, then a human settlement has to treat dust as a system-level threat from the very beginning. So why is dust such a serious problem on Mars? Because it attacks multiple parts of the system at once. First, it is mechanically bad. Fine dust can get into joints, seals, hinges, bearings, and moving surfaces. Once it gets in, it does not have to cause instant failure to become dangerous. Slow wear is enough. Extra friction is enough. One seal closing a little worse than before is enough. A mechanism that used to move smoothly but now sticks under load is enough. Over time, that kind of damage turns a routine maintenance into constant maintenance. Second, it is bad for sensors and optics. Dust reduces visibility in the atmosphere, and it also settles onto surfaces that need to stay clean. Cameras, solar panels, radiators, windows, instrument covers, navigation sensors, and external monitoring systems all become harder to trust when fine material keeps coating them. On Earth, dirt is annoying. On Mars, dirt is part of the operating environment, and the planet gives you a lot of it. Third, it is operationally persistent. This is not one storm and then a clean reset. Mars is a dusty planet all the time, and then sometimes it becomes much worse. That is what makes dust such a perfect Mars problem. It is always there in the background, and sometimes it scales up into a full mission threat. So the colony is not defending against one rare disaster. It is living inside a world made of abrasive powder, with wind strong enough to move it and static behaviour that can make it stick where you least want it. That combination is much worse than people usually picture. The danger is not just that you get dusty. The danger is that dust keeps reaching the exact surfaces and components you need to keep stable. The systems that make Mars livable are the same systems dust is good at degrading. And the hardest part is that dust does not stay in one category of damage. It links directly to power. This is where opportunity becomes the cleanest example. The rover did not fail because Mars suddenly became a different planet. It failed because the sky went dark too long. Sunlight dropped, the rover could not generate enough energy, temperatures fell, and recovery never happened. That is not just a rover story. That is a warning about any settlement that depends too heavily on solar power without major reserves and backups. Solar systems on Mars already face a difficult environment. Sunlight is weaker there than on Earth to begin with because Mars is farther from the sun. Then dust cuts into that budget again. Dust in the air reduces incoming sunlight. Dust on the panels reduces performance further. Long-duration storms increase opacity and lower generation for extended periods. So the problem is not only reduced efficiency on a good day. The problem is that Mars can suddenly turn an already difficult solar setup into an emergency. That has huge consequences for a colony. Power is not just electricity for comfort. Power runs life support. Power runs air processing. Power runs water systems, heating, communications, computing, medical equipment, food production, pumps, storage, and possibly local fuel generation. When power drops on Mars, it is not like a blackout in a normal city. It is pressure on the entire chain that keeps people alive. So a serious Mars settlement would need far more than a few solar panels and optimism. It would need surplus generation, large energy reserves, aggressive cleaning systems, redundant distribution, and probably non-solar baseload sources as part of the core design. Because a city that depends on clear weather on Mars is not a robust city. It is a city designed around hope instead of evidence, and dust does not stop at power. It keeps attacking everything else while the energy picture gets worse. Less light means harder operations. Poor visibility means more difficult travel, surface work, navigation and landing conditions. Dust coating radiators can hurt thermal control. Dust on seals can increase leakage risk over time. Dust on suits and equipment means contamination gets carried into air locks and workspaces unless cleaning becomes extremely disciplined. Dust on external hardware means inspection and maintenance loads keep climbing. Even simple outdoor tasks become more difficult when the environment keeps grinding fine material into the systems you depend on. That is why dust on Mars is better understood as slow-motion sabotage. It does not have to destroy everything in one moment. It just has to keep making every important system a little worse. Earth can survive storms because Earth's civilization is built on an environment that mostly supports life and infrastructure by default. Mars does not. On Mars, the default environment already hates your machines. Dust just makes that hate more visible. It reduces light, fouls seals, dirties radiators, wears bearings, degrades sensors, complicates landings, and raises maintenance demand across the whole settlement. And because dust is so common, you cannot treat this as rare bad luck. It becomes part of normal planning. That is one of the biggest reality checks in the whole Mars discussion. Every beautiful rendering of a Mars colony shows clean solar arrays, polished windows, bright habitats, and equipment that looks fresh out of the factory. Real Mars engineering has to assume the opposite. It has to assume the hardware is getting coated, scoured, clogged, and slowly degraded all the time. And once you accept that, the dream shrinks again. The colony looks less like a growing city and more like a maintenance problem that never ends. Not because people lack skill, but because Mars keeps adding friction to every system that matters. So dust is not weather on Mars. It is infrastructure sabotage built into the planet itself. It attacks power, movement, visibility, maintenance, and reliability all at once. And that makes the next problem even worse. Because once the dust gets onto everything, it is not just a mechanical issue anymore. It becomes chemistry, and Mars soil has chemistry that does not stay outside where you can safely ignore it. Perchlorate. That is the word that changes Mars soil from a farming problem into a human health problem. A lot of people say Martian soil like it is just dirt on another planet. That wording is too soft. It makes the surface sound passive, like all you need is water, fertilizer, and time. But Mars regolith is not neutral ground waiting for human use. It is chemically active material, and one of the biggest reasons is perchlorate salts. Phoenix identified perchlorates in Martian soil, And since then, NASA has treated them as a serious issue for human exploration. That matters immediately, because soil in a colony is never just soil. It sticks to suits, it gets trapped in joints and fabric, it rides in on boots and tools, it settles on surfaces, it gets into filters, it ends up near airlocks, work bays, storage areas and food systems. The moment people start moving around on Mars in any serious way, the ground comes back inside with them. So the chemistry of the soil is not some distant science detail, it becomes part of daily life. That is the first big correction. Soil is not only where you grow things. Soil is what your entire operation keeps touching whether you want it to or not. And that means perchlorates are not just a hazard during one dramatic accident. They are a routine contamination problem. A real colony needs routine more than anything. Routine means repeated entry and exit, rovers coming back from fieldwork, excavators moving regolith, cargo being unloaded, samples being processed, maintenance crews cycling through airlocks, dust on boots, dust on gloves, dust in hinges, dust in filters, dust near breathing zones and food systems. Once you picture that clearly, perchlorate stops sounding like a chemistry note and starts sounding like a habitat hygiene problem. Because the problem is not one person touching the wrong patch of ground one time. The problem is that the colony keeps interacting with regolith over and over again. Every excavation site becomes a contamination control site. Every rover track becomes a place where material gets redistributed. Every loading dock becomes a place where regolith is managed, cleaned, contained, or accidentally spread. Every airlock cycle becomes part of a public health system. That is what Mars keeps doing to the colony idea. It takes something that sounds simple and turns it into another industrial process. We will use the soil sounds easy. In reality, using the soil means building systems to isolate it, characterize it, clean it, process it, and control where it goes. The more active and industrial your settlement becomes, the more regolith handling stops being a side task and becomes one of the core health and operations problems. And this is where it is important not to oversell the science, because the honest version is already strong enough. Perchlorates do not mean Mars is instantly unusable. They do not mean life there is automatically impossible. NASA's own discussions around Phoenix made it clear that this kind of chemistry forces a reassessment rather than ending the whole story in one sentence. And that actually makes the problem more useful for this argument, not less. Because Mars is rarely one clean answer. It keeps giving you materials that look useful and dangerous at the same time. That is true here too. The same chemistry that raises human health concerns can also matter for things people want to do on Mars anyway. Perchlorates can be relevant to propellant chemistry, to oxygen extraction discussions, and to broader questions in astrobiology. So Mars does not hand you a simple label like good soil or bad soil. It gives you a complicated material that may be resource, hazard, and scientific clue all at once. That sounds exciting from a research standpoint. It sounds much less exciting when you're trying to build normal life around it. Because normal life depends on reducing complexity, not adding more of it. A stable settlement wants materials that are easy to use, easy to predict, and easy to keep separated from the human body when needed. Mars keeps giving you the opposite. The ground itself becomes something you cannot casually trust. You cannot just dig it, move it, pile it up and assume it is harmless because it looks like dust and dirt. The moment human lungs, water systems, agriculture, and long-term habitat cleanliness enter the picture, the chemistry matters. And once again, the dream starts shrinking under the real requirements. People love the line that humans will grow food in Martian soil. It sounds practical. It sounds like independence. It sounds like the beginning of a true colony. But once perchlorates enter the conversation, that sentence needs to slow down immediately. No, you are not casually farming the red dirt the way people farm a field on Earth. You're not walking out with a shovel and turning Mars into a normal agricultural landscape. You're pre-processing the material. You're isolating it. You are washing it or chemically treating it. You're buffering it, amending it and monitoring it. You're testing how it interacts with water, roots, microbes, equipment, and the closed environmental loops inside the habitat. In many cases, You may avoid direct use altogether and rely more on controlled media, hydroponics, or heavily treated regolith products instead of raw surface material. That is a very different picture. The fantasy version is settlers using local soil and slowly making Mars productive. The real version is an industrial chemistry workflow predicting to be a farm. Every kilogram of material has to be understood. Every use case has to be managed. Every contact pathway has to be controlled. Food production does not move Mars closer to a simple pioneer life. It moves Mars deeper into sealed, technical, expensive infrastructure. And that matters because agriculture is usually one of the biggest emotional shortcuts in the colony story. People here grow food locally and think that means the settlement is becoming natural. But on Mars, local food production does not become natural. It becomes another branch of life support engineering. You're not just growing plants. You're protecting the habitat from contamination, protecting people from exposure, protecting water systems from bad interactions, and protecting the crop system from unstable inputs. That is not agriculture in the ordinary sense. That is controlled biological production inside a hostile chemical environment. And the larger the colony gets, the harder this becomes. A small mission can be careful with a few samples and a few experiments. A larger settlement has more vehicles, more digging, more construction, more processing, more traffic, and more chances for material to move where it should not. Scale does not simplify the perchlorate problem. Scale spreads it. The more infrastructure you build, the more regolith handling becomes constant, and the more constant it becomes, the more serious contamination control has to be. That is another pattern Mars keeps repeating. Solutions create their own support systems, use local resources, and now you need local resource processing. Process local material, and now you need contamination control. Build agriculture, and now agriculture becomes part of a chemistry and hygiene system. Nothing stays simple for long. So when someone says the soil is there, so farming is just a matter of engineering, the real answer is harsher. Yes, it is a matter of engineering, but that is exactly the problem. On Mars, almost every hopeful sentence turns into a larger industrial sentence. Almost every simple plan unfolds into a chain of treatment, monitoring, isolation, and failure management. That is why the soil is not just dirt. It is another layer of the planet that fights the idea of ordinary human life. It does not simply sit there waiting to support you. It has to be studied, controlled, processed, and in many cases treated as a hazard before it can become useful at all. And once you accept that, even one of the nicest Mars talking points starts losing its comfort. Because people often say, Mars at least has water, as if that settles the argument. It does not. Water helps, but on Mars even good news comes with a new dependency attached to it. Mars does have water, and that is real good news. There is accessible water ice on Mars. NASA's swim mapping work has highlighted regions where buried ice may exist within the upper meter of the surface, about the top 3 feet. That matters a lot. Water is not just drinking water. It can support life support, oxygen production, hygiene, crop systems, radiation shielding mass, and hydrogen for the fuel chemistry. If you're trying to build anything on Mars that lasts longer than a short mission, water is one of the first things you want to hear about. And this is exactly the point where people expect the Mars story to become easier. Fine, the planet is cold, dusty, radioactive, and hard to land on, but it has water, so maybe this is where the whole argument softens. Maybe this is the resource that makes the colony finally start looking realistic. It does not. Because on Mars, the first question is never just whether something exists. The first question is whether it exists in the form, location, concentration, and accessibility that your survival system actually needs. And with water, that is where the comfort disappears. The ice is not spread across Mars in clean, convenient, colony-ready reservoirs. It is patchy. It depends heavily on location and latitude. It is one of the reasons landing site selection is such a difficult trade-off in the first place. Some places may be scientifically valuable, but bad for easy resource access. Some places may offer better ice potential, but come with worse engineering conditions, worse terrain, worse temperatures, or harder mission architectures. So the water problem is not solved by saying Mars has ice. That sentence is too simple to matter. The real question is much harder. Is there enough ice, shallow enough, pure enough, in the right place for the kind of settlement you actually want to run? That is the version that matters, because a colony does not need water as a concept. It needs water as a daily delivered input. It needs kilograms per day for drinking, more for hygiene, more for agriculture, more for oxygen production, more for industrial processing, more for fuel if local propellant becomes part of the architecture. And those flows cannot be occasional. They have to be steady. A settlement cannot live on geological optimism. It has to live on reliable extraction, and that is where the next hard reality hits. Even when the ice is there, it is not waiting for you as liquid water in a ready-made tank. It is buried in cold regolith. It can sit under overburden. It can be mixed with soil and frozen material that has to be dug, moved, heated, processed, separated, and handled. In other words, the challenge is not only finding water, the challenge is turning buried ice in a hostile frozen desert into a dependable daily utility. That distinction is everything. A lot of Mars talk quietly jumps from resource detected to resource available. Those are not the same thing. NASA's human exploration planning puts so much focus on mapping and characterizing accessible ice for a reason. The discovery is not the finish line. The extraction is the problem. The purity is the problem. The equipment reliability is the problem. The power demand is the problem. The maintenance burden is the problem. Once again, the hopeful sentence unfolds into a larger industrial sentence. To get water, you need excavation. Excavation on Mars means dust. It means wear on equipment. It means operations in cold conditions. It means machinery that has to keep working while the environment keeps trying to clog, freeze, grind, and contaminate it. It means thermal input to free water from icy soil. It means transport. It means processing. It means storage. It means redundancy. Because if water extraction stops, almost everything else starts failing soon after. That is why Mars has water does not save the colony story. It changes the colony story into a mining story, and not a mining story where you can slow down for a few weeks and catch up later. A mining story that can never stop. Your air depends on it if you are making oxygen from local resources. Your fuel may depend on it if you're producing hydrogen-bearing inputs for return systems or chemical processes. Your hygiene depends on it. Your food system depends on it. Your radiation strategy may depend on having water as shielding mass. Your emergency reserves depend on it. Your long-term confidence depends on the idea that tomorrow's water will arrive just as reliably as today's. That is not comfort, that is dependency. And dependency on Mars is dangerous because every dependency sits on top of another fragile layer. Water extraction needs power. Power systems are vulnerable to dust. Equipment needs maintenance. Maintenance needs spare parts. Spare parts need other cargo delivery. Cargo delivery needs successful landings. Landings depend on a difficult atmosphere and a narrow transportation chain. So even the best good news on Mars never stands alone. It is always tied to another chain of conditions that have to keep holding. That is why this section matters so much emotionally. On paper, water makes Mars look much more realistic. And it does help. It is a major resource. It is one of the few pieces of the Mars story that sounds like genuine support instead of pure punishment. But the second you turn that support into an actual colony architecture, the tone changes again. The colony becomes terrifyingly reliant on uninterrupted extraction from a planet that is bad at everything extraction depends on. The ice does not remove fragility, it reorganizes fragility around itself. Now the settlement has to protect dig sites. It has to maintain extraction hardware. It has to store and distribute water without losing too much to inefficiency or contamination. It has to keep the mining and processing chain alive during storms, cold periods, mechanical failures and power stress. It has to build backup capacity because losing local water is not a minor inconvenience. On Mars, losing water flow means losing the base. That is why this is one of the biggest emotional reversals in the whole Mars argument. Water makes the colony more feasible only by making it more dependent on a system that cannot be allowed to fail. So yes, Mars has water. That is true. It is important. It is one of the strongest arguments in favour of long-duration human presence. But it does not make the colony secure. It makes the colony dependent on a permanent extraction industry running inside a dusty, freezing, chemically hostile environment where almost every machine already has too much to do and too much can go wrong. That is not the same as having a river, a lake, or a living water cycle that helps sustain a world by itself. It is more like plugging your survival into a mine and praying the mine never stops producing. And once you say that clearly, the next question becomes unavoidable. If water and air both depend on industry, how close are we really to building that industry on Mars at meaningful scale? That is where one of the most famous Mars success stories has to be read much more carefully, because Moxie proved something important, but it also exposed how far away a real colony still is. Moxie worked, and that matters. It was real, it was successful, and it was an important step. Perseverance carried a small experiment called Moxie that took carbon dioxide from the Martian atmosphere and produced oxygen from it. NASA reported a total of 122 grams of oxygen produced on Mars, with peak rates of 12 grams per hour at 98% purity or better. That is a serious achievement. It means the basic chemistry is not just theory anymore. It works on Mars, in real Martian conditions, on a real mission. That is exactly the kind of result people point to when they say the path is opening up. And to be fair, that reaction is not completely wrong. Moxie is important. It proves that local resource use on Mars is not just science fiction language. You can take the atmosphere that is there, run the right process, and get useful oxygen out of it. That matters for breathing. It matters for industrial systems. It matters for future mission planning. It matters because every kilogram you do not have to launch from Earth is a big deal in Mars architecture. But this is also where the conversation usually becomes dishonest without even meaning to. A small success gets mentally expanded into a huge conclusion. 12 grams per hour is excellent science. It is tiny industry. That is the gap that has to stay clear. 12 grams per hour is not the air supply for a settlement. It is not a solved oxygen economy. It is not a rocket depot. It is not anything close to the continuous industrial output a real colony would need. It is proof that a much larger machine might one day work. That is very different from proof that a colony is now within easy reach. And this is one of the main ways Mars optimism gets smuggled into the discussion. A demonstration-scale machine succeeds, and people instantly talk as if city-scale infrastructure has become inevitable. But the gap between those two things is enormous. Moxie is not the bridge across that gap. It is the first piece of evidence that a bridge might be possible. That distinction is everything. A small oxygen experiment can fail occasionally and still be historic. A colony cannot. A small demonstration can run under controlled mission conditions and prove the process. A settlement has to run the process every day at far larger scale under much stricter reliability demands, with human survival tied to the output. That is not the same challenge with a bigger machine. It is a different level of responsibility. And the moment you say that clearly, oxygen stops being a hopeful science headline and starts becoming part of a giant industrial system. Because oxygen on Mars is not just for breathing. That is another place where people simplify too much. Oxygen's also oxidizer. An oxidizer makes up a huge part of the mass in many chemical propulsion systems. So the second you start talking seriously about making oxygen on Mars, you are not just talking about air and habitats, you are talking about return vehicles, surface operations, fuel architecture, and the entire logic of in-situ resource use. That sounds like progress, and it is, but it also raises the stakes immediately. Because now your survival and transport plans depend on scaling a whole chain of machinery that has to keep working on Mars. Now you need large-scale atmospheric intake. You need compressors that can run reliably in a dusty environment. You need heat management. You need electrochemical processing. You need power supply stable enough to support continuous operation. You need spare parts, diagnostics, maintenance cycles, and trained people who can keep the system alive when something drifts out of spec. You need long-duration reliability, because a colony cannot treat oxygen production as an interesting experiment. It has to treat it as a utility. And utilities on Mars are never just utilities. They are survival systems. That is why MOXIE is actually stronger evidence for how hard Mars will be than for how easy it will be. It shows the chemistry works, but it also shows how much more must exist around that chemistry before it means anything at civilizational scale. The machine itself is only the visible part. The real demand is the industrial ecosystem around it. People often talk about in-situ resource utilization like it automatically reduces dependence. In one sense, it does. Local oxygen production means fewer supplies launched from Earth. Local water extraction means fewer shipments from Earth. Local fuel components mean less imported mass. That sounds like growing independence, but on Mars, every new local capability also becomes a new dependency. Once your settlement architecture assumes local oxygen production, the oxygen plant cannot go down. Once your return plan assumes local oxidizer, the oxidizer plant cannot fail. Once your food, hygiene, and life support chain assume local water extraction, the water system cannot pause. So every time Mars gives you a possible local solution, it also creates one more industrial system that must run in a place that punishes failure. That is the pattern again. Every simplification becomes a support burden. MOXIE makes that impossible to ignore. It is a toaster-sized proof that a much larger plant could one day exist. But a larger plant is not just MOXIE, scaled up like a kitchen appliance made bigger. A much larger plant means much larger thermal loads, much larger power demand, much more wear, much more maintenance, much more integration with other systems, much more vulnerability to downtime, and much more pressure on the rest of the colony architecture. You're not scaling a gadget, you're scaling a chemical industry. And that matters because people still like to imagine Mars settlement in pioneer terms. A few brave people, some habitats, some greenhouses, some local adaptation, a new branch of civilization slowly taking root. But the deeper you go into the real requirements, the less that picture survives. Mars is not asking for hardy settlers with grit. Mars is asking for layered industrial systems that never stop running. That is the real lesson of MOXIE. It did not prove Mars colonization is easy. It proved that Mars colonization, if it happens at all, would be brutally industrial. You're not moving to a world and gradually adjusting to it the way people adjusted to new regions on Earth. You're taking a continuous chemical factory, launching it across interplanetary space, landing it through one of the hardest entry and descent environments in the solar system, assembling it in a freezing, dusty, chemically hostile place, and then relying on it to keep producing without major interruption. That is not a side feature of the colony. That is the colony. And once you understand that, a lot of the language around Mars starts sounding wrong. Settlement sounds too soft. Homesteading sounds almost absurd. Even city starts sounding misleading because a city suggests background stability. Mars gives you almost none of that. What it gives you is a long chain of tightly linked industrial processes where one failure can spread into everything else. Air is not free, water is not free, fuel is not free, thermal stability is not free, radiation protection is not free, agriculture is not free, even dirt is not neutral. So the more honest the Mars plan becomes, the more it stops looking like human expansion and starts looking like permanent systems engineering under constant environmental pressure. That is why MOXIE is such an important turning point in this argument. It is a true success, and it should be respected. But if you read it honestly, it does not tell you Mars will become normal. It tells you normality on Mars would have to be manufactured continuously at scale, with industrial reliability so high that failure stops being just a technical issue and becomes a direct threat to life. And once you accept that, the next problem gets even more unsettling. Because even if you solve air, water, fuel and shielding, you still have one biological question hanging over the whole planet that nobody can answer with confidence yet. Mars gravity may be enough to let you walk around. It may still be too little to let you remain fully human for life. Mars gravity sounds like one of the few comforting numbers in this entire story. It is about 0.38 of Earth's gravity, not 0g, not the Moon's much weaker 0.16g. So people hear 38% and think that sounds survivable. You could walk, you could lift more, you could move equipment more easily. It feels like a compromise that might actually work. Not Earth, but maybe enough. That's exactly why this problem is so dangerous. The number sounds reassuring before you ask the only question that matters. Enough for what? Because NASA's own human health discussions are blunt about this. The long-term physiological effects of living continuously in Martian gravity are still largely unknown. That is not a minor gap in the data. That is one of the biggest unanswered biological questions in the entire Mars idea. People talk about landing systems, habitats, oxygen production, radiation shielding, and surface power. As if gravity is the one thing Mars gives you for free. It does not. Mars gives you a gravity field that might be enough to let people function for a while, and might still be too weak to support permanent human life in the way a real colony would need. That difference is massive. Space medicine already knows a lot about what happens in microgravity. We know astronauts lose muscle, we know they lose bone, we know the cardiovascular system adapts in ways that are not helpful when returning to stronger gravity. We know body fluids shift. We know red blood cell changes happen. We know the human body starts rewriting itself when gravity drops too far for too long. The body is built for loading. Remove enough of that loading and systems begin to degrade. But Mars is not microgravity, and that is what makes it harder, not easier. Because now you're in the zone we do not understand well enough. Not weightless, not Earth normal, not obviously safe, just different enough that people can tell themselves maybe it will be fine. Maybe is not a civilizational plan. The real question is whether 0.38 grams is above the threshold needed to protect the human body over very long periods. Not over a 6-month mission, not over one exciting expedition, over years, over decades, over pregnancies, over childhood development, over aging, over generation after generation of people who are not visiting Mars but living there for life. That is a completely different level of risk. Some NASA summaries have noted that researchers often argue more than 0.5 G may be needed to provide enough bone loading for long-term protection. Mars sits below that speculation line, and that should hit much harder than it usually does, because if the safe threshold really is somewhere above Mars gravity, then the colony problem is not just engineering anymore. It is that the planet itself may sit in the wrong biological range for permanent human settlement. That is a terrifying place to put the future of a civilization. And this is where the conversation has to become personal instead of abstract. A mission can survive uncertainty. A colony cannot. A mission can send healthy adults, monitor them, rotate them home, and accept that some unanswered questions remain because the exposure is temporary. A colony is not temporary by definition. A colony is where bodies are supposed to spend their whole lives. It is where adults are supposed to age. It is where children are supposed to grow. It is where pregnancy, infancy, development, puberty, injury recovery, and old age all have to unfold under local gravity, not Earth gravity. So the question is not whether an astronaut can walk around on Mars, smile for a camera, run a few experiments, and come home after a year. That would be impressive, but it would not settle the colony question. The colony question is whether human beings remain strong, fertile, durable, medically stable, and developmentally normal at 0.38 G across the full span of life. Right now, nobody knows. And that ignorance is much more serious than people want it to be. Because if you do not know whether a place supports normal human development, then calling it a future home is already too confident. You can call it a destination, you can call it an outpost, you can call it a research base. But the word colony quietly assumes that biology will cooperate if engineering is good enough. Mars gravity is one of the clearest places where that assumption may fail, and notice how this keeps happening. Every time Mars seems to offer one useful advantage, the fine print gets worse. It gives you gravity, but maybe not enough. It gives you an atmosphere, but barely. It gives you water, but only if you mine it constantly. It gives you local oxygen production potential, but only through heavy industry. It gives you solar, but the chemistry fights you. Mars keeps giving partial support with a hidden cost attached. Gravity may be the harshest version of that pattern because you cannot engineer around it easily at planetary scale. You can build shielding over a habitat, you can process water, you can clean dust off hardware, you can try to scale oxygen production, but you cannot thicken Mars' gravity. You get what the planet gives you, and the minute you take that seriously, the settlement starts changing shape again. Because if Mars' gravity might not be enough, then now the colony needs even more machinery just to protect its own people from the place they are trying to live in. Maybe large centrifuges for regular gravity loading, maybe rotating habitat sections, maybe constant exercise programs far beyond what people imagine for normal life, maybe medical protocols built around bone density, muscle maintenance, cardiovascular stress, developmental monitoring and long-term health surveillance. Maybe children cannot even be safely raised there until decades of evidence say otherwise. Maybe pregnancy in Mars gravity becomes one of the hardest medical questions in the whole settlement. That is what happens when the real data enter the room. The simple picture dies again. Instead of a self-sufficient city, Mars starts demanding a biomedical support system layered on top of the life support system, layered on top of the power system, layered on top of the extraction system, layer-wise on top of the landing system. The colony keeps getting pushed away from normal life and back toward controlled survival under permanent supervision. And that is the hidden cost of the gravity problem. Not just that the answer is unknown, but that the unknown sits at the center of the human future there. A bad answer would not just make Mars uncomfortable, it would make Mars biologically unsuitable for permanent open-ended settlement in the way the word colony usually implies. That is why this is one of the most important lines in the whole argument. Mars is not merely far away, it is biologically unvalidated for permanent human life. You can build around radiation, you can build around dust, you can build around thin air, you can build around toxic soil. But if the gravity itself is wrong for long-term human flourishing, then the dream never becomes normal no matter how advanced the machines get. It stays what it has been all along. A managed environment where human beings are trying to hold themselves together in a place that may never fully support them. And if that still sounds theoretical, the next section makes Mars feel even less calm. Because people like to describe Mars as a dead world, as if dead means stable. It does not. Mars is not alive enough to help you, but it is not dead enough to leave you alone. Mars gets talked about like a dead world, and that can make it sound safer than it really is. People hear ancient planet and picture stillness. They picture a surface that has already done all of its violence and now just sits there waiting for engineers to arrive. But that is not the right picture. Mars is not Earth in terms of tectonics, oceans, or a thick atmosphere driving constant large-scale change, but it is not some perfectly quiet stone either. InSight recorded more than 1,300 Marsquakes before the mission ended. NASA science reports also highlighted a magnitude 4 event linked to a meteoroid impact. That matters because it breaks the comforting idea that Mars is basically a frozen museum piece. You do not need Mars to behave like Earth for this to become a settlement problem. You only need it to be active enough that the ground, the subsurface, and the impact environment still matter. And that is exactly the point. A colony cannot treat Mars like a decorative backdrop. It has to respect the fact that the planet still shakes, still gets hit, and still reveals things by force. That changes the engineering mindset immediately. A quiet-looking surface can make people lazy in how they think. They start imagining habitats placed on stable plains, tunnels drilled into reliable ground, storage buried under regolith, infrastructure spread out with confidence. But once Marsquakes are part of the picture, even if they are not constantly catastrophic, the surface stops being something you casually trust. Now the ground has mechanical behavior. Now the subsurface matters. Now local geology is not just a science target, it is a safety issue. And that's important because Mars keeps punishing casual assumptions. The danger is not that every day brings disaster. The danger is that over time, enough processes are still active that nothing important should ever be designed as if the environment is truly finished changing. Then the impact story makes this even sharper. One of the most striking in-situ-era results was that a significant impact exposed buried water ice closer to the equator than previously seen. From a science perspective, that is exciting. It tells you something important about where water may exist and how the subsurface is arranged. From an exploration perspective, it is useful intelligence. But from a colony perspective, it is also a reminder that Mars is still being physically reworked by incoming objects. It is still being excavated. It is still being reshaped in local ways that matter. That should change how you hear the word ancient. Ancient does not mean inactive. Ancient means the planet has a long history, and parts of that history are still interacting with the present. Impacts still happen. Material still gets exposed. The surface is still being modified. The archive is still being edited. And that matters because a colony is not just visiting for a few weeks. A colony is trying to turn that environment into routine. It is placing habitats, power systems, landing zones, storage sites, roads, excavation areas, maybe fuel plants, maybe underground shelters. It is building assumptions into the ground. So if the ground is still part of an active system that gets shaken and struck, even occasionally, then the colony is not settling into geological retirement. It is building on top of a world that still has ways to surprise it. That is the deeper problem with Mars in general. It does not have enough living planetary activity to help you the way Earth does, but it still has enough physical activity to create risk. Earth's dynamism supports civilization in many ways. Atmosphere, water cycle, thick air, magnetic field, active geology, recycling systems, abundant energy flows. Earth is dangerous too, of course, but it is also deeply supportive of life and infrastructure overall. Mars does not give you that support. It does not give you thick air, rich hydrology, fertile open landscapes, or a naturally protected biosphere. It takes away most of the helpful systems and still leaves enough motion in the background to keep your engineering under pressure. And once you frame it that way, Phobos becomes even more important. Because now Phobos is not just one weird moon with a bad orbit. It becomes part of a larger texture across the whole Mars system. Small bodies matter there. Debris matters there. Ejecta matters there. Impact gardening matters there. Material exchange matters there. The planet still gets hit. The moon is still decaying. The atmosphere still grows and shrinks seasonally. Dust still moves around the surface and through the air. And the ground still shakes enough to demand respect. None of that means Mars is in chaos every day. That is exactly what makes it more dangerous for long-term settlement thinking. If the place were violently catastrophic every week, the answer would be simple. You would just reject it. Mars is worse in a more complicated way. It is usually calm enough to tempt you and unstable enough over time to punish that temptation. The problem with Mars is not that it is constantly exploding. The problem is that it keeps stacking moderate instability on top of a planet that is already missing the protections and resources human life wants most. So even when something seems manageable by itself, it joins a larger system of friction and risk. A Marsquake alone might be manageable. Dust alone might be manageable. Thin air alone might be manageable. Radiation alone might be manageable with enough shielding. Toxic soil alone might be manageable with processing. But Mars never gives you one thing alone. It gives you all of them in one place, linked together, with a transport chain from Earth that is slow and expensive and late by design. That is why this section matters. It reshapes the basic intuition people carry into the Mars debate. A lot of people think dead means safe. Dead does not mean safe here. Dead just means the planet no longer does the big life-supporting work that Earth does. It does not mean the planet has stopped being physically real. And physical reality is enough to keep a colony under pressure. The ground can shake, the sky can fill with dust. The subsurface can surprise you. The impact environment can expose new resources and new dangers at the same time. The inner moon can decay over millions of years in full view above your infrastructure. The atmosphere can change seasonally. None of those things have to be dramatic every day to matter. They only have to keep being true in the background while your city tries to become normal. and normal is exactly what Mars keeps refusing to give you. So the line that matters here is simple. Mars is too dead to help you, but not dead enough to leave you alone. That may be the worst combination for settlement. A planet that does not nurture you, does not protect you, does not stabilize your biology, does not make farming easy, does not make arrivals routine, and still occasionally reminds you that it can shake, strike, erode, expose, and rearrange things on its own schedule. That is not a partner in civilization. That is an environment you are constantly negotiating with. And once you see Mars that way, the next problem stops sounding technical and starts sounding social. Because even if you solve the hardware, the dust, the water, the oxygen, and the shielding, the people inside the system still have to function with a level of autonomy and isolation no civilization has ever really practiced. Mars can be close enough to talk to and still too far away to help. That is one of the most important things people miss when they picture a Mars colony. They imagine Earth as mission control in the background, always watching, always ready, always one call away. That is not how Mars works. Signal delay between Earth and Mars is not a few seconds. Depending on where the planets are in their orbits, one-way communication delay is about 4 to 24 minutes. In some crude mission studies, once you are near Mars, the delay can be above 21 minutes one way. And during solar conjunction, when the sun gets in the way, communication blackouts can stretch much longer. That one fact destroys a huge amount of comforting fiction. There is no joystick colony. There is no real-time coaching from Earth when something starts going wrong. There is no surgeon on Earth walking a medic through a crisis as if they are in the next room. There is no ground team taking over instantly when a fire alarm goes off, or a system starts behaving strangely. By the time Earth hears the problem is already old. By the time Earth sends advice back, the people on Mars have already acted, or failed to act, on their own. That means every emergency happens mostly alone. And that is not just a communication detail. That changes the whole structure of civilization on Mars. Because the moment help cannot arrive in real time, control changes, responsibility changes, risk changes. The people on Mars stop being an extension of Earth and start becoming their own final authority, whether they are ready or not. Even the robots prove this point. NASA does not drive Perseverance with a joystick. Engineers cannot sit on Earth and steer it live, because the delay makes that impossible. They build a plan, they upload commands, they wait, and the rover executes later. That is for a machine doing exploration work. Now scale that reality up to a human settlement. A habitat fire does not wait 12 minutes for advice. A depressurization alarm does not pause because mission control is still reading the incoming data. A radiation shelter call during a solar event does not sit there politely while Earth debates options. A contaminated water loop, a power distribution fault, a medical emergency, a soup breach, a fuel plant failure, a landing accident, a psychological breakdown inside a confined crew, none of these problems happen at Earth speed. They happen at Mars speed. And Mars speed means the people inside the colony are already the ones in charge before Earth can even join the conversation. That is what makes Mars not just physically far away, but decision far away. And once you understand that, the colony starts looking different again. It is not only a technical outpost, it is a forced experiment in local judgment. Governance, safety culture, command structure, crew selection, training, medical capability, maintenance discipline, conflict management, and crisis leadership all become more important because the ground truth is simple. The people there will have to decide first and justify later. That pushes the human side of Mars into much harsher territory than people usually admit. NASA delay studies and autonomy research keep pointing in the same general direction. The longer the communication delay, the more tactical responsibility shifts away from Earth and onto the crew. That means higher onboard autonomy, more authority in the habitat, more need for local expertise, more cognitive load, and more pressure on small groups living in isolation. You cannot have a colony that depends emotionally and operationally on immediate support from Earth, because immediate support does not exist there, and that changes people. On Earth, when teams work under pressure, there is usually a larger system around them. More people, more specialists, more hospitals, more spare parts, more institutions, more backup. Even in dangerous jobs, most workers still operate inside a civilization that can surge support toward a problem quickly. On Mars, that cushion disappears. The crew becomes the first responder, the maintenance division, the local government, the medical team, the conflict resolution system, and the final emergency authority all at once. That is a level of operational autonomy no civilization has ever practiced at that distance under those conditions. Because Mars is not just remote, it is remote while being lethal. It is remote while every person is living inside life support machinery. It is remote while the environment outside is trying to kill the habitat through radiation, dust, cold, low pressure, and equipment wear. That means the psychological load is not just isolation. It is isolation with consequences. Every argument matters more. Every mistake matters more. Every leadership failure matters more. Every weak procedure matters more. And that is where the Mars dream stops being only about rockets and starts becoming about human systems under extreme stress. How do you govern a place where Earth cannot take tactical control? How do you handle authority when a local commander may have to make irreversible decisions before outside experts can respond? How do you manage conflict in a group that cannot simply separate and go home? How do you run medicine when evacuation is not realistic on normal emergency timescales? How do you train people not just to do jobs, but to absorb responsibility that on Earth would be spread across whole institutions? That is the real social architecture of a Mars colony, and almost nobody talks about it with the seriousness it deserves. Because this is not just a transportation problem, it is a civilization design problem. The colony would need people with technical skill, emotional stability, conflict tolerance, discipline, and judgment at a level far beyond what most normal communities demand. It would need rules that work under delay. It would need command systems that do not collapse under stress. It would need a culture that can survive confinement, repetition, danger, grief, and long periods without immediate outside reassurance. And the harder truth is that even if you build all of that well, the emotional reality still stays cold. On Earth, when systems fail, civilization rushes in. Fire crews come, hospitals respond, specialists join the call, replacement hardware can move, supply chains reroute, agencies coordinate. Friends and family can often reach you the same day. That is what living inside a functioning civilization feels like. You're surrounded by backup even when you do not notice it. On Mars, civilization is 4 to 24 light minutes away, and sometimes operationally farther than that. During some communication conditions, it is not just delayed, it is functionally absent in the moment that matters most. So from the colonist's perspective, there is no real backup in the Earth sense. There is only whatever redundancy they already built, whatever procedures they already rehearsed, whatever spare parts they already stored, and whatever emotional stability they already brought with them. That changes the moral weight of the whole idea. A colony is often sold as backup for humanity, a second branch, a safeguard, a way to make human civilization less fragile. But from inside the colony, it would not feel like backup. It would feel like being cut loose with a toolkit, a command structure, and a survival system that has to keep working because rescue is too slow to count. That is why the isolation on Mars is not just loneliness. It is operational finality. You do not get instant correction. You do not get instant rescue. You do not get instant reinforcement. If your water system starts failing, you are the water system team. If your habitat catches fire, you are the fire service. If someone gets badly hurt, you are the emergency room. If leadership breaks down, you are the government. If the group starts to fracture psychologically, there is no outside society stepping in fast enough to absorb the shock. That is not normal expansion. That is human life pushed into a level of autonomy and separation that sounds exciting in theory and much harsher in practice. And once you face that honestly, the final escape route people always reach for starts looking weaker too. Because whenever Mars gets too difficult, someone says the same thing, fine, then we will just terraform it. That is where the story gets even harsher, because terraforming does not rescue the colony idea. It exposes how much the planet is fighting you from the start. Terraforming is the line people use when Mars gets too hard to defend. The moment the real problem starts stacking up, someone says the same thing. We will thicken the atmosphere. We will warm the planet. We will fix the pressure problem. We will deal with radiation. We will release trapped gases and make Mars more like Earth. It sounds like a way out. It sounds like the big solution that makes all the smaller problems temporary. But that only works if you pretend Mars is a basically habitable world that just needs a push. It is not. Mars did not simply lose a nice atmosphere and then wait politely for us to put it back. Mars spent billions of years becoming the planet it is now. NASA's MAVEN mission exists because one of the key scientific questions is how Mars lost so much of its atmosphere to space over time. And modern measurements still show atmospheric loss happening today. Solar wind stripping continues at around 100 grams per second on average, and it gets stronger during solar storms. That does not mean Mars is emptying out overnight. It means the planet's long-term story is not atmospheric stability. It is atmospheric loss. That changes the whole framing. Terraforming is usually described like a giant engineering project. Add gases, warm the world, let the pressure rise, let the surface become easier to live on. But Mars is not just sitting there with a full set of easy ingredients waiting to be unlocked. The planet in front of you is what remains after immense spans of cooling, escape, and chemical trapping. The atmosphere is thin because Mars became a planet that could not hold on to a thick, protective atmosphere the way Earth did. That is not a small setback. That is the deep history of the world you're trying to turn into a home. Then you hit the next problem, and it is even more basic. Inventory. Before you even argue about giant mirrors, imported volatiles, artificial greenhouse schemes, orbital shades, or any other mega engineering concept, you have to answer a simple question. Where is the material coming from? The atmosphere Mars has today is thin, unstable across the seasons, and mostly carbon dioxide. Mars once had much more water and a thicker atmosphere, but what you are looking at now is the leftover world after billions of years of planetary decline. So terraforming is not just a matter of technology. It is a matter of whether the raw materials needed for a much thicker, warmer, more stable environment actually exist in accessible amounts and in usable forms. That is a brutal problem because the argument often skips right over it. It treats Mars like a machine with a setting you can change, turn up the pressure, turn up the heat. But the planet is not a machine waiting for a new setting. It is the residue of a very long process that moved in the opposite direction. Terraforming is not asking Mars to become slightly more convenient. It is asking Mars to become a different kind of planet than the one it has spent eons becoming. That is why the idea sounds so powerful and so evasive at the same time. It is not really solving the current colony problem. It is moving the real colony problem so far into the future that people stop checking whether it still makes sense on any normal human timescale. And that matters because this is where honesty about colonization either survives or collapses. If your Mars colony only becomes plausible after planetary-scale atmospheric reconstruction, then the colony is not plausible in any ordinary civilizational time frame. That is the real conclusion terraforming often hides. It turns a present-tense engineering and survival problem into a vague future promise that nobody has to cash out in detail. But the science we actually have does not point toward just warm it up. It points towards something much harsher: thin carbon dioxide air, weak shielding, high radiation, buried and patchy resources, toxic soil chemistry, dust-driven maintenance, low gravity with unknown long-term biological effects, difficult entry, descent and landing, slow communications, constant industrial dependency. Those are not signs of a world on the edge of becoming naturally habitable. Those are signs of a world that keeps forcing you back into enclosed habitats, buried shelters, controlled ecosystems, heavy processing and endless support systems. Terraforming does not cancel that. It exposes it. Because the moment you need a whole planet rebuilt before the colony starts sounding normal, you've admitted the key point without saying it directly. Mars is not naturally close to being a second home. It is so far from being one that the escape plan requires remaking the planet itself. And even then, the deeper pattern does not go away. Mars does not become easier at scale. It becomes more expensive at scale. More machinery, more energy, more material movement, more industrial dependence, more things that must keep working across longer periods under worse conditions. On Earth, scale often creates resilience because the environment supports the system. On Mars, scale often creates more exposure because the environment keeps pushing back. That is the truth underneath the entire video. Mars colonization is already doomed not because no human will ever stand there. Humans absolutely can stand there. Outposts are possible, missions are possible, bases are possible, long stays may be possible, but that is not what the word colony promises. Colony promises permanence, colony promises growth, colony promises self-sustaining normal life, colony promises that the place stops being an emergency and starts being a world people can truly belong to. The science keeps killing that promise. Phobos is falling inward. The orbital environment is not quietly stable. The sky barely protects you. The atmosphere is too thin to shield you and too thick to ignore. Radiation keeps adding damage day after day. Dust keeps attacking power, visibility, seals, sensors and machines. The soil fights your biology. Water helps, but only if mining never stops. Oxygen can be made, but only through serious industry that cannot fail. Gravity may still be wrong for permanent human life, and nobody can say with confidence that multi-generational settlement at 0.38 G is medically safe. Communication delay means every crisis happens mostly alone, and the big escape hatch, terraforming, only proves how far Mars is from supporting normal civilization on its own. That is why the hardest line in this whole argument is also the simplest. Mars is not a second home. At best, it is a place where humans may build managed outposts, run difficult missions, extract science, and maybe maintain a presence for some period of time with enough machinery, discipline, and cost. But that is not the same thing as a true colony. That is not a self-sustaining branch of civilization living in ordinary continuity. That is a permanent emergency managed by technology, and that is the verdict. Mars colonization is already doomed because the word colony says more than the planet can honestly support. Mars does not give you a stable foundation and ask for patience. It gives you a long list of compounding failures and asks whether you can keep them all from linking up at once. That is not the beginning of a normal world. That is the maintenance of an unnatural one. Humans may visit Mars. Humans may build on Mars. Humans may survive on Mars for a while. But living there as if it is the next Earth is the part that breaks. The science does not support a second home. It supports a managed emergency that humans can reach, endure, and maybe hold for some time as long as the machines keep winning. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.